So more examples related to electromagnetic induction. As you can see in this figure, we have a permanent magnet which is next to a circuit that contain a coil and a galvanometer. So we have a solenoid, a circular wire, permanent magnet is there, suggests a metal from which a magnet is made up of. So magnetic material, permanent magnets, which material we use to make a permanent magnet? So we use steel. The next part, the magnet is moved to the left. So what we did, we moved this magnet towards the left hand side and inserted a small distance into a coil. So this magnet is moved and it moves into the coil. The galvanometer deflect briefly and shows that there is a current in the coil. Explain why there is a current in the coil. So what is the reason for that? Why there is a current? So when the magnet is moved, towards the solenoid, even it is moved towards or away, there is a change in magnetic field. But in this example, as a magnet is moved towards the solenoid, there is a change in magnetic field. And due to the change in magnetic field, whenever there is a change in magnetic field, it induce or it produce EMF, or you can also say current. So whenever a circuit is complete, there will always be a current. So you can write, when the magnet is moved towards a solenoid, there's a change in the magnetic field, and due to a change in magnetic field, there is always an induced EMF. So use the screen annotation, state what pole will be induced here. Use the screen annotation, state what pole will of a for a solenoid, what pole, north or south, will be induced on at Q, and other side, what pole will be here on this side of a solenoid. So it will be a north pole, that's right, and the opposite side will be a south pole. So as the magnet is moved, in the question, as the magnet is moving near the coil, the end Q of a coil behave as a magnetic pole. State the polarity and explain why it has polarity, like why there is a north pole there. So first we'll mention, 1 mark is for mentioning north, as you already identified on the figure, that there will be a north pole. And what is the reason for that? The solenoid will try to or induce current So the current induced or the current produced in solenoid will try to oppose the change in magnetic field. So that is the reason, and it can only be oppose the change by appearing opposite pole, by appearing a like identical pole, because we are moving a magnet towards, so strength of a magnetic field is increasing. What solenoid will try to do? It will try to oppose the change in magnetic field. And how it can oppose the change in magnetic field? By producing a pole in same direction, like pole. Then suggest 2 ways in which the deflection of a galvanometer can be reversed. How I can change, like example, say when I was moving the magnet towards, example, it was deflected towards the right hand side. I want to change the direction of deflection. I want to change the direction of induced current. So what I can do, there are 2 ways to change the direction of induced current. We already discussed in the last session. What were the 2 ways? Number one, we can move the magnet away because, or first we were moving towards, so we can move the magnet away or opposite direction as the original. That is first thing. And then we can change the pole of the magnet. Like first, north pole is facing the solenoid. Now the south pole should face the solenoid. And if even it is inserted, it will produce a current in opposite direction. Another question. In this question, we have two ends of a metal rod. So this is a metal rod are connected to by a copper wire. So they are connected by a copper wire. You can see here, and there's a sensitive ammeter. The rod is placed horizontally. So we place the rod horizontally in the magnetic field, north and south poles of a permanent magnet. So you can see the north and south pole. The rod is moved upward at a constant speed as shown. So if rod is moved upward, first, if I say, can you draw an arrow to show the direction of current? So how you can draw an arrow to show a direction of current? So your first finger, the index finger, point towards the south. So in this example, in this figure, in this question, the south is on my right hand side. So I will point towards south. My thumb should point in the direction of the movement. So thumb is pointing upward. Where my finger is pointing towards the screen or into. So if I say draw an arrow to show the direction of the current. So what will be the direction of the current? That direction of the current will be into. So first finger is pointing south, thumb is pointing the direction of the motion of a wire, and second finger is pointing in the direction of induced current. So the rod is moved upward and there is a current. An induced EMF is there in the rod. State two factors which determine the size of induced EMF. Like how we'll know how much induced EMF is produced or what is the value of the induced EMF. So it depends on uh, the strength of a magnet, or it depends on the speed of the movement of wire. And second thing, it depends on strength of a magnet. And third thing, it depends on length of a wire in a magnetic field. If we have greater length of a wire in a magnetic field, then more induced EMF will be there. Then the size of a current in ammeter depends on size of induced EMF. State one other factor on which the size of current depends. Like how much current produced, that depends on how we are changing a magnetic field, and what else the current produced depends on. It depends on the resistance of this wire or resistance of the rod. Because if a rod is having more resistance, then current produced will be smaller. If rod is having a less resistance, then current produced will be higher. So we can mention indirectly, we can mention resistance, we can mention size of the wire, because longer wires have more resistance. So that also decide. So all the factor leads to a change in resistance. So the current produced depends on how we are changing a magnetic field, as well as the resistance of the wire. If wire is having a low resistance, yeah, that's right. If we are using a longer length, the resistance will be higher, so current will be less. If we are same thing, if we are using a thinner wire, it will have a high resistance, so low current will be produced. Now in this one, the direction of a motion of a rod is now changed. First, in the previous figure, we were moving it upward, but now we are moving sideways towards right or left. So what happened? Look, between the magnetic poles, there is a constant magnetic field. When it goes out from the pole, like if I draw a 2D, this is a 3D figure, but if I draw a 2D, two dimension. So example, this is a 2D image and a magnetic field is from north to south. So between the magnetic pole, there is a constant magnetic field. And when we move away from the magnetic pole, the strength of a magnetic field is decreasing. So if I have a wire, example, this pink dot example is representing a wire. So if I'm moving the wire up or I'm moving a wire down, so it means there is a change in the magnetic field because the wire is like cutting a different field lines. Here, there will be a change in the magnetic field, so it will induce EMF. But if I move the wire right or left, what will happen? Because there is a uniform magnetic field, there is a constant magnetic field. Between the poles, there's a constant magnetic field. So if I move towards the right or left, so there is no change in a magnetic field. So there is no induced EMF. So wire, the idea is that the wire should move perpendicular or it should cut the field line. If a wire is moving along the field line, it does not produce a magnetic field. It does not produce a current. So it should cut the field line to produce a current. So the answer here that there is no change in a magnetic field. So the induced EMF is 0, or there is no induced EMF. So always remember that the wire should cut the magnetic field, should cross the magnetic field. If it is moving along the magnetic field, there is no induced EMF because there is no change in magnetic field. Figure 9.1 shows a thin straight rod which is XY placed in a magnetic poles. So there is a rod which is placed in a magnetic poles. The wire, the wire from end X and Y are connected to a 0 center voltmeter, as you can see in the figure. There's a 0 center voltmeter. When X and Y is moved slowly upward, so we are moving it upward. Can you draw an arrow to show the direction of induced current using a Fleming's right-hand rule? Can you state a direction of an induced current using a Fleming's right-hand rule? The first finger is pointing towards the south. Index finger should point towards the south. So your index finger should point towards the south and your thumb is pointing up. So what should be the direction of induced current for this figure? The wire is moving up. This is a motion of the wire. As I mentioned, that this is a motion of the wire. The wire is going up. And we want to find...
the thumb will go up.
Yeah, means that, yeah, that's true. Like index finger, my index finger should point on the right-hand side because south is on the right-hand side. My thumb should point upward. So thumb is pointing upward, index finger is toward the right. Where my finger is pointing. So my finger is pointing towards the screen or into the screen. So what will happen? That the current, the induced current is from Y to X. So it will move in this way.
Yes, miss.
Is it clear to everyone? The direction of induced current? But that was not the main question. This is just as an example. I asked you to identify the current. The question state how X and Y must move to produce a large deflection in opposite direction. So we want to produce a large deflection. That is one thing. So if we want to produce a large deflection, means we should move faster. And we want to produce a deflection in opposite direction. So if we were moving upward, now the wire should move downward. So what is the answer here? That we should move the wire faster. That is one thing, because if we move the wire at a higher speed, there will be a large deflection. But because the deflection should be in opposite direction, So we should move opposite direction. So move the wire at high speed in opposite direction, or move the wire at high speed downward. Because first we were moving upward. So if I want the direction of a current to be opposite, so I should move it downward. So, and if I apply the rule here, you can clearly see that when I apply the rule, if I am moving the wire downward, that is the red arrow is representing the motion of the wire. So my index finger should point towards south, and the index finger is pointing towards south, and my thumb should point downward. So my thumb should point down. So index finger is towards the right hand side, thumb is pointing downward. Where my finger is pointing, it is pointing out of the screen. So if my finger is right hand, the second finger is pointing out of the screen. So it means the current will move from X to Y. So it will be in opposite direction. Now, the second part, X and Y is now rotated about a center point. X is raised up and Y is lower. Explain why there is no deflection. So now what they're doing, they're changing the motion of, first they were moving the whole wire up or either moving whole wire down. But now they're rotating, they're changing the position of X and Y. So X is going up and Y is going down. So this is a new position of X and this is a new position of Y. The question is why there is no deflection. Because what happened, see, if X is going up and Y is going down, so the direction of induced current will be opposite. Like example, if X is going up, it produces a current. If X is going up, it produces a current in this manner. And Y is going down, so it produces a current in this manner. So they produce the current in opposite direction. As a result, they produce a current in opposite direction. What will happen if I say like, or you can also understand from this that X is going up, say the current is like this, and Y is going down. So example, current is like this. So both are producing a current in opposite direction. So what is the resultant current, the total current? If I say 2 ampere is on the right hand side and 2 ampere is on the left hand side, and there is one wire. So what they will do, they will cancel out each other and there will be 0 ampere. So as a result, there is no induced current. So the answer for the last part, that when X is move up and Y is moving down, why there is no induced current? So, or why there is no deflection? So X and Y produce current due to change in magnetic field in opposite direction, which cancel out so no deflection or does not produce deflection. And if this same wire, if there example, if there was a question that the wire is moved toward the right or left, in that case also there will be no induced current, because that time magnetic field is not changing. When we are moving the wire up and down, there is a change in magnetic field. But when we are moving right and left between the poles, there is no change in magnetic field. In figure 8.1 shows a bar magnet inserted into a coil. A north and a south pole of a bar magnet are marked. So can you identify the pole which is produced on this side? What pole will be there on for a solenoid? Use the screen annotation. Yes, that's right. So north will be on the, because magnetic field is strength increasing, so it will try to oppose. So north is on the left and south is on the right. That's right. Then explain why the galvanometer deflect as a bar magnet is being inserted into a coil. So the idea is of 3 marks. look what happened when when a magnet is moved. Sorry. There is a change in a magnetic field which induce EMF and produce current which cause deflection. So when the magnet is moved, there is a change in magnetic field. Change in magnetic field induce EMF in the solenoid. As a result, it produces a current and which cause a deflection. Explain what determine the direction of the reading on the galvanometer. So it depends on direction of the movement of the magnet. 2 marks are there. So 2 things it affects: direction of magnet, movement of the magnet, like either magnet is moved towards or away, and the pole of the magnet facing the solenoid. The pole of the magnet facing a solenoid, if north is facing or south is facing, that will produce a different direction of induced current. A bar magnet is held with a north pole inside one end. Figure 10.1 shows a coil connected to a galvanometer that has a 0 mark in the center. The magnet is pulled horizontally towards the right, so we take out the magnet away. So as we take out the magnet away at a constant speed, there is a large speed through a large distance, like we move this magnet far away. So when it is far away, means there is no magnetic field will be there, as it is the magnet is too far. There will be no magnetic field, so the induced current will, there will be no magnetic field, there will be no change in magnetic field, so it will be 0. State what happened to galvanometer reading as a time passes. So as we are moving it away, there is a change in magnetic field, it induces EMF. But with the passage of a time, and it is moved at a constant speed, so it remain constant for some time and return to 0. Why it return to 0? Because when we are moving a magnet away, there is a constant change in a magnetic field, so there is a fixed voltage produced here. But once the magnet is too far from the solenoid, there is no there is no magnet placed here, so there is no magnetic field. That's why what will happen, the reading on the galvanometer will be 0. Then in the next part, as a magnet moves, a north pole is produced on the left hand side. Explain why north pole is moved on the, it is basically what happened, we are moving the magnet away. So if we are moving the magnet away, the magnetic field strength will start to decrease. So what pole will be induced here? So south pole will be induced here and north pole will be here. But the question is why north pole is produced here? So the current produced in the solenoid will try to oppose the change in the magnetic field. So the strength of a magnetic field is decreasing. Solenoid produce opposite poles to attract. So I don't have a space to write, but that idea is the same. That whenever there is a change in magnetic field, there is always an induced EMF. An induced EMF is always try to oppose the change in magnetic field. And if the magnetic field is decreasing, it will try to increase. If magnetic field is decreasing, it will try to increase, or opposite increase, it will try to decrease. Figure 9.2 shows a magnet that is held just below a vertical connected to a galvanometer. The magnet is released. So we release the magnet. Like the magnet, because of gravitational pull, it will go down. State any effect on the galvanometer. What will be the effect on the galvanometer? There will be the galvanometer will show deflection. Due to change in magnetic field. And return to zero. Why it will return to zero? Because as the magnet is falling, it will move away from its magnetic field, the solenoid. So as magnet may be too far from a solenoid, so there will be no induced EMF. So there will be a deflection first, that's right. And the galvanometer will show a zero as there is no magnetic field being cut. That's good, Basant. State any effect on the magnetic field produced by the coil. So state any effect of a magnetic field produced on the coil. What will be the effect of a so any effect on the magnetic field produced by the coil, it will produce magnetic field or changing magnetic field to oppose the solenoid. So it will be there, change in a magnetic field, and it will try to oppose the movement of the magnet. A similar question, a magnet is being held by a spring and the lower end of a magnet is pushed down. So what we did, we pushed down the lower end of a magnet. The lower end of a magnet is pushed down into a upper end of a coil and it is held rest. During the movement, the EMF is induced and the meter show a deflection to the right hand side and then it returned to zero. So here the needle deflected on the right hand side or towards the right hand side and then it returned to, so original deflection is toward the right and then it returned to zero. So when we are moving a magnet downward, deflection is towards right and then we stop. So there's no change in magnetic field, it returned to zero. Explain why the EMF is induced, the same answer, because there is a change in the magnetic field. Or we can also say the coil cuts the magnetic field, change in magnetic field or cuts the magnetic field, both having a same meaning. Then state what happened to a needle of a meter when the magnet is released from rest and it is being pulled up. So when the magnet was going down, moving down, the needle was deflected towards the right. But now they're saying the magnet is being pulled up by a spring. If this magnet is being pulled up, so if we change the direction of the motion of the so what will happen to the reading on the galvanometer? If it is deflected towards the right when it was going down, so now it will deflect towards left when it is going up. So magnet is released and so the needed the magnet is released from rest and is pulled up by a spring, what will happen to a deflection? So it will deflect in opposite direction or left. The magnet continue to oscillate up and down. So the magnet is moving up and down. What will happen to deflection on the galvanometer? That will also, because if the magnet is moving up and down, there's a continuous change in magnetic field and in opposite direction. So what it causes? It causes a galvanometer reading to deflect as well. So the needle will deflect right and left, or it will oscillate between the two extreme, right and left.